Hey everybody, just wanted to wrap up our unit on derivative analysis with a video here on optimization. So it's kind of this little extension or enrichment topic that we have during this unit. And what I have in this video are two examples, one that involves finding a maximum value and the other involves finding a minimum value. And I structured this video a little bit different than usual. Rather than me sort of teaching and writing and taking the time to express every step and to show all the work, I actually have a full solution key presented here, and I'm just going to sort of read through or talk through the work and some of the concepts and some of the ideas. The hope is that that'll save a little bit of time and it won't lead to a really lengthy video, that you'll be able to kind of just get the idea of kind of how these optimization examples work. So with that in mind, let's jump in. Here's example one, finding a maximum volume. You can see a number of different pictures here of boxes, and the manufacturer wants to design this box with no top, an open box. It has a square base and a restricted surface area of 108 square inches. And the idea here is to try to figure out what kind of dimensions will produce the box that has the maximum volume. So we call a problem like this an optimization problem. And with these optimization problems, you're going to look for two equations. One equation is going to be that equation you're trying to maximize or minimize. In this case, we're trying to maximize volume. So the volume of the box would be length times width times height, or since the base is square, let's just use x for one of the dimensions of the base. So we'll call that x squared times h. But then there should be a secondary equation, and that secondary equation involves a restriction. In this problem, the restriction is that we only have 108 square inches of surface area. So in the situation that we're given here, the surface area can be calculated by using x squared for the base, and then the four lateral walls would be simply x times h. So I have a volume equation of x squared times h, we'll call that the primary, and then the surface area equation of x squared plus 4xh. So now I've established my primary equation and my secondary equation. Now, the idea with the secondary equation, the one with the restriction, is that I'm going to try to use and manipulate that equation and somehow plug that into the primary, because I want to get the primary equation all in terms of a single variable. Right now, my volume equation is in terms of x and h. Can I solve for h and therefore plug in or substitute an expression to get my primary equation all written in terms of a single variable? And so the work that you see here on the screen is just me doing just that. So I have the 108 plugged in for SA, that's the restriction, and I'm solving for h. Once I do, I have the expression right here that I'm going to substitute into the primary equation for h. After all that's finished, I have a volume equation, that's the primary that we're trying to optimize. The volume equation is x squared times this expression, simplified down becomes 27x minus 1/4 x cubed. If you'd like to pause the video and work out that algebra or kind of see where it all comes from, this would be a great time to do so. As always, I'd like to encourage you to do that at any time. So now I have the volume equation in terms of a single variable, and that's a great first step. It's always good to know if we have any kind of restrictions on the domain. In this case here, of course, we have to have a positive dimension, so I can't have an x dimension that's less than 0. But then also the square base has to be, the x squared has to be less than 108, since I have 108 square inches for the entire surface area of the box. So keep in mind that my valid x solutions, my valid dimensions, must fall between 0 and the square root of 108. All right, now, we're looking to maximize this volume function. So in calculus, the way we do that is we find the derivative and set it equal to 0 to find critical points. Let's do that now. Find the derivative of v, or v prime, or dv dx, and we'll get a 27 minus 3/4 x squared, set that equal to 0, and solve to find your critical points. Now the critical points I found here are plus and minus 6, but remember that only positive 6 would fit on that domain. And so what I did is I built a sign chart on v prime, and I found that at x equals 6, the volume, or v prime I should say, the derivative of volume changes from positive to negative, which proves that volume is maximized when x equals 6. So here's my conclusion. A maximum on V, on volume, occurs when x equals 6. My reasoning, because V prime, it changes from positive to negative. And by the way, the problem, I believe, asks for the dimensions. So if x equals 6, the base would be 6 by 6. But then what would the height be? I'd have to plug 6 in here for x and then solve to get my h height of 3. So there's my box of 6 by 6 by 3 inches that would yield the maximum volume along with keeping that restriction of 108 square inches of surface area. Now, that's a maximizing problem. Let me show you one other optimization problem that involves finding a minimum. So here is an example, and this example involves developers that want to create these sort of these 3-room motel structures. And it says here to lower construction costs. Of course, the company wants to have the minimum total wall lengths, but at the same time, you can't have really cramped hotel rooms, so you want to make sure that the rooms have at least 400 square feet of floor space. And that's kind of up here in the paragraph at the top. And so here's just 3 examples of some possible motel constructions right here. So we have, looks like a 20 by 20. What if x was 20? What if y was 20? I have horizontal walls and I have vertical walls. Or what if we went with 40 by 10s or 10 by 40s? In the red boxes, you see the total number of feet in linear wall length. And again, the idea here is to keep costs down. We want to minimize the total length of all the walls in this construction project. Well, again, for optimization, you want 2 equations. You want to figure out an equation that's the primary for what you're trying to optimize, minimize, or maximize. And after that, we need to find a restriction equation. We'll call that the secondary equation. So just to kind of repeat the process for you here, in this case, our goal is to minimize the wall length. So let's try to write a function or a formula for the wall length. And I'll use x's for the horizontal wall lengths. I'll use y's for the vertical wall lengths. So what would be that equation that we're trying to optimize? Well, in this case, it would be L. I'll use a capital L for wall length. 6x plus 4y. I have 6 horizontal walls, and then I have 4 vertical walls. So 6x plus 4y. Now, the secondary equation would be my restriction right here, that the area, x times y, has to be 400. If that's true, then I could solve for y and say that y equals 400 divided by x. Substitute that 400 over x in for y so that I now have an equation, L, in terms of, or as a function of, one variable x. So here it is, 6x plus 1600x to the negative first. There's my equation. I want to optimize that, or find its minimum in this case. So let's find the derivative and set that derivative equal to 0. Let's take a look here. The derivative would be 6 minus 1600x to the negative second. And here's my algebra where I'm setting it equal to 0 and solving. Notice this, though, that I have an x critical point where the derivative L prime does not exist, and that happens when x equals 0. And then I have plus or minus 16.3 for my other critical points. But remember, think of your domain. The only valid critical points here would be, or point I should say, would be the positive 16.330. I can't have an x, a wall dimension of 0. I can't have a wall dimension that's negative. So we're just going to go with the positive 16.33. And then just to justify the conclusion, I'm going to build a L prime sign chart, and sure enough, I see that less than 16.33, my derivative is negative. Greater than that number, the derivative goes to positive. So what I have found is that at x equals 16.330, there's a minimum on the function L because L prime changes from negative to positive. So let's use that information to find the remaining dimension. If y equals 400 over x, I can plug in 16.330, my critical point, to find the other dimension to be 24.495. And there it is, the wall dimensions of 16.330 by 24.495 feet will minimize my total wall length structure. There's the minimum total, and that will also maintain that restriction of having each room be 400 square feet. So that's pretty much what optimization is all about. You have a primary equation you're trying to maximize or minimize, find the secondary restriction equation, and figure out a way to write that primary equation in terms of the single variable. Write a derivative, set it equal to 0 to find your critical points, and then complete your analysis using any one of our calculus methods for justifying extrema. And that, again, is what optimization is all about.